All right, welcome to the information for how to graph systems of equations. So we're going to be working on today. We've been working with how to graph linear equations. Now we're going to take it another step further and learn how to graph a system of equations that are straight lines and tell how many solutions a system has and how to evaluate those systems in the context of a word problem. So we're going to be looking at the standards. Before we had graphed linear equations. So today what we're going to do is determine the number of solutions to a system of linear equations and solve a system of linear equations by making a graph. So the first thing is our vocabulary. First thing we need to know is what is a system of equations. A system of equations is when we have at least two equations that contain at least two different variables. So remember when we have a linear equation, we have both an x and a y variable. Right? So a system of equations is at least two equations that contain at least x and y. Okay, so we're going to be looking just today at two linear equations. So each of our equations is going to have an x and a y value. So that's what makes it a system, is that we've got two equations that have two different variables. Now the next thing that we look at is when we talk about the solution to a system of equations. The solution is the point or points on those equations that contain values that make both equations true at the same time. So the solution is the set of values x and y that works in both equations that were given. And we're also going to look at the types of systems that we have. We have consistent versus inconsistent systems and independent versus dependent systems of equations. No solution was an inconsistent system. So since the graphs are parallel, there is no solution and the system is inconsistent. And so now we're going to use the graph to determine whether the system is inconsistent or consistent if it's independent or dependent. So for these two lines, what we've got is y equals x minus 3 and y equals negative x plus 1. So again, if I were to put these on a graph, I would use y equals mx plus b. So in this case, my y-intercept for the first line is negative 3. So I start my slope at, or my point at negative 3 on the y-axis. And my slope is whatever is being multiplied by x. So again, in this case, we have a slope of 1 times x. So from negative 3, I'm moving up 1 throughout the line. So up 1 on the x-axis, up 1 on the y-axis. For the second equation, my y-intercept is 1, so that graph starts up at 1. But in this case, my slope is, since it's negative x, remember there's a 1 there, so it's actually going to be negative 1x. So in this case, my slope is starting at positive 1 and going down across the graph. So I've got two equations, y equals 1x minus 3 and y equals negative x plus 1. And what I see is that I have two lines. Since I looked at these equations here, I see that they have different slopes, so that tells me that they're going to intersect at some point. Okay. So since I have two lines that intersect at a single point, that's one solution. And that means that our system is consistent and independent. They intersect at a point, so there is exactly one solution, and it's consistent and independent. All right, so for this one, we've got a graph of actually three lines. Y equals x plus 4, y equals x minus 1, 2y plus 3x equals 6. For this first problem, they want you to look at the two lines, 2y plus 3x equals 6, which is this line here, and y equals x minus 1, which is the line over here. So you're only looking at these two lines for this particular problem. So looking at those two lines, what type of system Are we looking at consistent and independent, inconsistent, consistent and dependent, or it cannot be determined? All right. And the correct answer is that it's consistent and independent because these two lines intersect at a single point. So there's one solution, which is a consistent and independent system. All right, so using the same graph, let's try another one. This time we're looking at the two equations, y equals x plus 4, which is this line here, and y equals x minus 1, which is this line over here. So looking at those two, just those two lines, what type of system do those two lines form? Consistent and independent, inconsistent, consistent and dependent, or it cannot be determined. And the correct answer is that this is an inconsistent system. And that's because y equals x plus 4 and y equals x minus 1 are parallel lines. And how do we know that they're parallel? Because they both have the same slope, 1 times x, and different y-intercepts, plus 4 and minus 1. So they start at different points and they have the same slope, so those are two parallel lines, which means they will never intersect, which gives me an inconsistent system. All right. Next, we're going to graph a system of equations, determine whether the system has no solution, one solution, or infinitely many solutions. And if the system has one solution, we're going to name it. So the two equations that we're looking at are y equals 2x plus 3 and 8x minus 4y equals negative 12. So it's looking at these two equations. If I want to graph them, what I need to do is make sure that both of them are in the right form. Y equals mx plus b. So if you look at the first system, or the first equation, y equals 2x plus 3, that's already in slope-intercept form, y equals 2x plus 3. So we don't need to do anything to this equation, y equals 2x plus 3. We do, however, need to rearrange 8x minus 4y equals negative 12 into the correct form. So we need to take the 8x minus 4y and we need to rearrange it so that it's just y equals everything else. So the first thing I need to do, I'm going to take this 8x and I need to remove it. So from 8x, if I have 8x, I need to take it away. And because this is an equation, I took away 8x from this side, which means I need to take away 8x from the other side of the equation also. And so that gives me negative 4y equals negative 8x minus 12. So now my equation has, we're almost there, we've got negative 4y, so I need to remove the negative 4. So I'm going to divide by negative 4. Since I'm multiplying negative 4 times y, in order to cancel that out, I'm going to divide by negative 4. And since I divide this side by negative 4, I need to divide both terms on the other side by negative 4 also. So negative 8x gets divided by 4, and negative 12 gets divided by 4. All right, so when I divide everything by negative 4, what do I get? Negative 4 divided by negative 4 is y. Negative 8 divided by negative 4 is positive 2. And since I have x, it's 2x. And 12 divided by negative 4 is negative 3. But since I was subtracting here, subtracting negative 3 makes this a positive 3. So what do you notice about this line over here? I notice that the slope is 2 and the y-intercept is 3. And this equation, once I rearranged it into slope-intercept form, this has a slope of 2 and a y-intercept of 3. So this line and this line have the same slope and the same y-intercept. That makes them the same line. So when I graph those, they're both going to be the exact same line. Y equals 2x plus 3 and 8x minus 4y equals negative 12 are the same. They're just written in two different forms. Okay, so this equation is the same as this equation, which means that any combination of x and y that works for this equation will also work in this equation. So when I see my graph here, it's all the same line. So the correct answer is that for this particular system, the graphs coincide, so there's an infinite number of solutions to this system of equations. Whatever works for x and y in the first equation will also work for x and y in the second equation. All right, let's take a look at another one. We're going to do the same thing, solve the system of equations by graphing and determine how many solutions it has. And if it has a solution, we're going to name it. So x minus 2y equals 4 and x minus 2y equals negative 2. So just like the last one, right, we're going to write both equations in slope-intercept form. So we need to rearrange both equations so that that's y equals mx plus b. Okay, so we're going to solve both of these kind of simultaneously. So I'm going to do x minus 2y equals 4. The first thing I need to do is I need to take the x away from this side of the graph, or side of the equation, because I want just y by itself. So I take x away there, and I'm going to take x away from the other side. Over here, same thing. I've got x minus 2y, so I'm going to take away the x that's there. And that's going to leave me with what on both sides? On this side I took away the x, so what's left is negative 2y equals negative x plus 4. On the other side, negative 2y equals negative x minus 2. So my next step, I've got negative 2 times y, so I'm going to divide by negative 2. And since I divide this side by negative 2, I need to divide everything on the other side also by negative 2. Go to my other equation, negative 2 times y, so I'm going to divide by negative 2 over here. And once again, take both terms on the other side and divide those by negative 2 also. So when I do that, negative 2 divided by negative 2 cancels out, so I'm left with y equals, and this was negative x. Again, if it doesn't make sense to you, there's a 1 here. So it's negative 1x divided by negative 2. So when I divide negative 1 and negative 2, I'm left with positive 1/2, because a negative and a negative makes a positive. So 1/2 x, and 4 divided by negative 2 is negative 2. So my new equation, y equals 1/2 x minus 2. I go to my equation on the right. Again, the negative 2's will cancel, so we're left with y. That's equal to, again, there's a negative 1 here. So negative 1 divided by negative 2 is actually going to be positive 1/2 x plus 1. So these two equations, y equals 1/2 x minus 2 and y equals 1/2 x plus 1, what do you notice? Well, what I noticed was when I'm going to go graph these, this equation has a slope of 1/2 and this equation has a slope of 1/2. So they have the same slope. This equation has a y-intercept of negative 2. This one on the right has a y-intercept of positive 1. So they have the same slopes but different y-intercepts. So that tells me that those two lines are going to be parallel. So y equals 1/2 x minus 2 starts at negative 2 on the y-axis, and the slope is up 1 and over 2. Up 1 and over 2. Second equation starts at positive 1 on the y-axis, and the same slope, up 1 and over 2. So these two lines are parallel, which means they will never intersect. So since they're parallel, they do not intersect, and there will be no solution. Since there's no point of intersection, there's nothing that will work for both the first and the second lines at the same time. So there's no solution to this system of equations, which if you look at this makes sense, right? Over here I've got x minus 2y, and down here I've got x minus 2y. That's the same thing, right? Well, up here x minus 2y is equal to 4. Down here though, that same thing is now equal to negative 2. So how could the same thing be equal to two different values? Well, it can't. That's why there's no intersection. There's nothing at any point where this side, x minus 2y, could be both 4 and negative 2. Okay, so now you're going to get a chance to do it. You're going to graph these two equations, y equals 2x plus 3 and y equals 1/2 x plus 3, and say whether there's no solution, one solution, or an infinite number of solutions. And if the system has one solution, identify it. Right? And so the correct answer is one solution. So looking at the graph here, y equals 2x plus 3 and y equals 1/2 x plus 3, I notice that since they have different slopes, right, those lines are not parallel and they're not the same. So there's going to be just one solution. There's one point of intersection. I take the equation y equals 2x plus 3 and I use that to graph it. I start at 3 on the y-axis and my slope is 2 over 1. So it's going up 2 on the y-axis as I go over 1. So this line here represents 2x plus 3. All right, my other equation also starts at 3 on the y-axis, but its slope is 1/2. So it's going up 1 and over 2. So it's right here. And as you can see, those two lines intersect at the y-intercept for both lines, at 3. So my solution is that there's one solution, and it's 0, 3. 0, 3 is the one combination that works for both of those equations at the same time. Okay. Let's try another one. X plus 3y equals 4, and 1/3 x plus y equals 0. How many solutions does it have? And if it has one solution, go ahead and name it. And the correct answer is that there's no solution. And why is that? Well, if we rewrite each of these equations, x plus 3y equals 4, if I rewrite that into slope-intercept form, so x plus 3y equals 4, first thing I need to do is move the x to the other side. So I need to take the x away from here and move it to the other side of the equation. So I've got 3y equals negative x plus 4. And then to figure out what y is, I divide by 3. So then I've divided both of the values on the other side by 3 also. So my equation is that y equals negative 1/3 x plus 4/3. That's an x. Right. So this first equation is y equals negative 1/3 x plus 4 over 3, which is right here on the top. Right. Here's that equation for to graph it. My second equation, I'm starting with 1/3 x plus y equals 0. So 1 over 3 times x plus y equals 0. So to solve for y, I need to move the 1/3 x to the other side of the equation. So I take it away from there and I move it here. Negative 1/3 x. Right, so my equation is that y is equal to negative 1/3 x plus 0. And I don't need to write the plus 0, but it helps to identify it in this case. So what do I notice between these two lines? Well, for the first equation, I have a slope of negative 1/3. For the second equation, I have a slope of negative 1/3. So they have the same slope. For the first equation, the y-intercept is 4 over 3. And for the second equation, the slope is 0. So they have the same slope, but different y-intercepts, which means that the lines will be parallel. There's no intersection, so there is no solution to that system. All right, let's take a look at a word problem. How can we use this in a real-world situation? So the situation that we're dealing with is that Naresh rode 20 miles last week and plans to ride 35 miles per week. Diego rode 50 miles last week and plans to ride 25 miles per week. Predict the week in which Naresh and Diego will have ridden the same number of miles. So in this, there's a lot of information that we can use in this particular problem so far. First thing that you'll notice is that we actually have two variables that we're dealing with. We're dealing with the total number of miles that each of them is going to ride in a certain number of weeks. Okay. So we're dealing with the number of miles that they're riding and the number of weeks. So since we have two different variables, we need to, or two different things we're trying to find, we need to use two different variables. So we're going to have both x and y, and what we want to do is identify what each x and y is measuring. Okay, so x, since we're doing miles per week, x is going to be the number of weeks that they're riding. You can assume that they're riding bikes here. Okay, so x is the number of weeks. 1 week, 2 week, 3 weeks, 4 weeks, and so on. Y is the number of miles that they're going to ride. All right, so x is weeks and y is miles. Right, so let's write two equations for each situation. So we've got Naresh and we've got Diego. How can we represent the number of miles that Naresh is riding and the number of miles that Diego is riding? So the number of miles that Naresh is riding, remember that's going to be y. So for Naresh, what do we know about Naresh? Well, we know he rode 20 miles last week. So he's starting at 20 miles to get to his total amount. And every week after that, he's going to ride 35 miles. So that means in 1 week, he'll go 35 miles. 2 weeks, he'd go 35 and 35 for a total of 70. 3 weeks, 35 plus 35 plus 35. So we don't want to have to keep saying 35 plus 35 and so on. We want to simplify it. Well, I can get that value by doing 35 miles times x, however many weeks. Right? So if x is 1, he rode 35 miles. If x is 2 weeks, he rode 70 miles. So we take the miles that he started with, 20, and add 35x. What about Diego? Diego's in the same situation in that he rode a certain number of miles, but he rode 50 miles the previous week. And from there, he's only going to ride 25 miles per week after that. So 25 times x, the number of weeks. So for Naresh, our equation is that y is equal to 20 plus 35x. For Diego, it's y equals 50 plus 25x. Right. And this kind of visualizes what we just talked about. If y is the total number of miles, right, for Naresh, that's 35 times the number of weeks, x, plus the 20 that he had before. For Diego, it's 25 times x plus the 50 that he started with. So we have two equations, both using x, the number of weeks, and y, the total number of miles. All right, so looking at the two equations this way, we're going to look at a graph eventually, but first what I want to point out is how we can use tables also to solve these types of systems. All right, so if we take a look at Naresh over here and Diego over here, right, we're going to make a couple of columns. So remember, we've got x is the number of weeks, y is the number of miles. Right, so we're just going to make a table to calculate how many miles Naresh and Diego are each driving or riding based on the number of weeks. Right. So for Naresh, before they started doing the same number of miles each week, Naresh started with 20 miles, okay, whereas Diego started with 50 miles. Okay. After the first week, how much does each of them have? Well, after that first week, Naresh increased his total amount by an additional 35 miles. So if he had 20 and he rode another 35, he's up to a total of 55 miles. Diego over here, he increased his total amount by adding 25 miles to his total. So he started at 50, added 25 to it, so now Diego is at a total of 75 miles. So looking at that, after 0 weeks, they weren't at the same amount. After 1 week, are they at the same amount? No, not yet. So we're going to keep checking. So they ride another week. Another week goes by. How many is each of them at? Well, again, Naresh rode another 35 miles. So we add another 35 miles to his total. So 55 and 35 makes 90. So after the second week, Naresh has ridden 90 miles. Diego finishes week 2, and he has increased his total by another 25 miles. So 75 and 25 means that Diego's total is now at 100 miles. So are those the same yet? No, so we need to keep going. So another week goes by. Naresh, after week 3, increases his total by another 35 miles, which brings his total up to 90 plus 35, or 125 miles. Diego increases his amount with another 25 miles. So now his total is 100 plus 25, which brings him to 125 miles. So looking at that, after week 3, did you notice they've both ridden 125 miles after 3 weeks. So even though they started with different amounts, right? Naresh started with only 20 miles, Diego started with 50. At the end of the 3rd week, because Naresh was riding more miles each week, he caught up to Diego, and now after 3 weeks, they both have ridden 125 miles. So that's how we can solve this, by just creating a table and using the y-intercept and the slope in each case. What does that look like on the graph? Well, it looks like this. The blue line here is Naresh. Notice he starts with 20 miles, and then after the 1st week, he's now up to 55, which is what we found in our table. After the 2nd week, he's up to 90. After the 3rd week, he's up to 125 miles. So it matches, the blue line matches the table that we made here for Naresh. For Diego, he starts at 50 miles, and after the 1st week, he's up at 75. The 2nd week is now up to 100. Again, what we found in our table. The 3rd week for Diego is at 125. And notice that's where those two lines intersect on the graph. Okay. Notice they both intersect right there at 125 miles, and it's at week 3. So week 3 is 125 miles. So the point of intersection for those two lines gives us our solution as to when those two systems measuring how many miles they rode, right, at what point are those two going to be the same? It's at week 3, and it's 125 miles. Now we can double check this. We kind of did it already, but we can take that solution, 3 and 125, and check each equation. Does it make it true? So remember, for Naresh, the number of miles was 35 times the number of weeks plus 20. For Diego, it's the number of miles equals 25 times the number of weeks plus 50. So if we say the number of miles is 125 and the number of weeks is 3 in both cases, does it give us a true statement? Well, 35 times 3 is 105, plus 20 is 125. 25 times 3 is 75, plus 50 is 125, so this does work out in both cases. So the solution means that in week 3, Naresh and Diego will have ridden the same number of miles, which is 125. All right, so you're going to go ahead and do this one here. Alex and Amber are both saving money for a summer vacation. Alex has already saved $100 and plans to save $25 per week until the trip. Amber has $75 and plans to save $30 per week. In how many weeks will Alex and Amber have the same amount of money? All right, so I'll help you set it up a little bit here at first. Again, just like before, we want to identify what our two variables are. We've got X and Y. So X is going to be measuring the weeks, and Y is going to be measuring the amount of money that each person has saved. So we'll say X or Y is the amount of money saved. Right. So you're going to want to write two equations using x and y to compare how much Amber and Alex have saved after a certain number of weeks, and then identify at how many weeks will Alex and Amber have the same amount of money. And the correct answer is 5, and you can kind of see it over here on the graph. So the two equations that you should have come up with for Alex, he started, his total amount, right, was $100 that he starts with, plus the amount that he saves, which is 25 per week, x. Okay. So Alex is this line here, this top line. He starts at $100, and he's going up by 25 each week. Right. For Amber, her amount starts with $75, and she is saving $30 each week. Right. So she starts here at $75, and her graph goes up by $30 each additional week. Okay. And what we'll see is that as we continue this graph, those two lines will intersect right here at week. We'll go down to the x-axis to measure the weeks, 5. And at that point, each of them will have $225. So that point of intersection tells me that after 5 weeks, Alex and Amber both have $225 saved. All right, and that brings us to the end. Hopefully it makes a little bit of sense as to how to graph systems of equations and what that solution to a system tells us. The solution to a system of equation tells us the values that work in both situations. So a system of equations is at least two equations that have at least two variables, and the solution is what values make both equations true at the same time.